In machine learning, we're pretty much always walking a tightrope. On one side, you've got a model that's so simple it just misses the point completely. And on the other, you have a model that's so ridiculously complex it gets totally lost in the details. Today, we're diving deep into that balancing act, the constant crucial battle between underfitting and overfitting.
And this question, this is really the heart of the entire challenge, isn't it? It's one thing to build a model that can just memorize a bunch of answers it's already seen. But the real magic, the whole goal, is to create a model that can generalize, one that can correctly answer questions it has never, ever seen before. So here's our game plan. First, we're going to define what we're actually trying to do when we talk about learning. Then we'll get into the two big pitfalls, underfitting and overfitting. After that, we'll zero in on that perfect sweet spot right in between them and talk about the surprisingly simple principle that helps us find it.
Okay, so what is the real goal here? It's not just about acing the practice test, right? A truly successful model has to perform well on brand new, unseen inputs. And that whole concept is called generalization. The key metric we use to measure this is called generalization error, or sometimes you'll hear it called test error. Basically, it tells us how well our model is going to perform out in the wild, on data it was never trained on. And let me tell you, this is the number that truly matters. And that brings us to a really critical and often kind of painful distinction. A model's performance while you're training it can look amazing, just deceptively high. But how it performs in the real world can be a totally different story. Understanding and closing that performance gap is the absolute key to building a useful model. And here's the fundamental conflict. Look on the left, you've got training error. We can see it, we can measure it, we can work directly to push that number down. But on the right is the test error, how the model will actually do on new data. This is what we truly deeply care about, but it's like a black box. We can't look at it while we're training. So any successful algorithm has to pull off two things that are often in a tug of war with each other. First, you got to make that training error small. You have to actually learn from the data. But second, and this is crucial, you have to make the gap between its training performance and its test performance as small as possible. You have to make sure what it learned wasn't just a fluke. All right, so let's dig into the first major way this can all go wrong, underfitting. This is what happens when our model is just, too simple to even begin to grasp the real patterns in the data. We call this underfitting. And I think the best way to think about it is like a student who barely studies for a big test. They don't really get the material, so of course they're going to do poorly on the practice questions and they're going to bomb the final exam. The model is just too simple. It completely fails to learn. The telltale sign of underfitting is super simple. Both the training error and the generalization error are really high. The model is failing on the practice test and on the final exam. It's a flashing red light that tells you the model itself just isn't powerful enough for the job. Now, on the complete other end of the spectrum, we've got the opposite problem, and this one is often much, much trickier to spot. This is the danger of creating a model that is way, way too complex. This is overfitting. In our student analogy, it works perfectly here too. This is the student who doesn't just learn the concepts, they memorize the exact wording of every single practice question. So they get a perfect score on the practice test. But then when the final exam asks the same questions in a slightly different way, they completely fall apart. The model hasn't learned the signal. It's just memorized all the noise. And this, right here, is the classic sign of overfitting. The training error is incredibly low. It looks like the model is a genius, but the generalization error is sky high. There's this huge gaping chasm between its practice performance and its actual real-world performance. So we've got underfitting over here and overfitting way over there. How in the world do we find the balance? Well, this brings us to this really important idea of model capacity. You can think of a model's capacity as just how flexible or complex it is. A simple straight line has really low capacity, while a huge, deep neural network has an enormous capacity. Our goal is to find that Goldilocks level of capacity, powerful enough to learn the real patterns, but not so powerful that it starts memorizing every little random detail. Okay, this graph you're looking at is honestly one of the most important charts in all of machine learning. See that cyan line? That's our training error. As we increase the model's capacity, make it more complex, the training error just keeps going down and down and down. That makes sense. But now look at the purple line, the generalization error. It goes down at first, but then it hits this minimum point. That's our sweet spot. And then it starts to climb back up. That climbing part, that's overfitting, right there in action. So let's just put the two extremes side by side to lock it in. An underfit model is too simple, and it fails everywhere. An overfit model is too complex. It aces the training data by memorizing noise, but it fails on new data. See the common theme? Both of them result in high generalization error, and that's exactly what we're trying to avoid.
So how do we actually guide our model to that sweet spot? Well, the solution is actually surprisingly old, drawing on a classic principle from philosophy and science that's been around for centuries.
Yep, Occam's razor. The basic idea is that simpler explanations are generally better than more complex ones. So if you have two different models that both explain the training data pretty well, you should probably prefer the simpler one. Why? Because it's way less likely to be overreacting to noise and much more likely to have captured the true underlying pattern. So, in machine learning, we apply Occam's razor using a whole set of techniques called regularization. It's basically our way of programming a preference for simplicity right into the learning algorithm itself. So how does this actually work in practice? It's pretty clever. We actually change the model's goal. Instead of only trying to get the training answers right, we add a complexity penalty to its score. So now the algorithm is playing a whole new game. It has to find a balance between getting a good score on the training data and keeping its own complexity as low as possible. And that's really the key takeaway here. Regularization acts like a guide rope. It gently pulls our high-capacity model away from that dangerous overfitting zone and back towards the sweet spot on that U-shaped curve, right where it generalizes the best. It's how we find the balance.
But this leaves us with a really fascinating final question, doesn't it? We've spent this whole time making the case for simplicity. And yet, the most powerful models in the world today, deep neural networks, are defined by their absolutely massive, staggering complexity. So how can both of these things be true at the same time? Well, that is a fantastic story for another time.